Supervised learning and unsupervised learning are two fundamental paradigms in machine learning, and the difference between them comes down to one key question: do we have labeled answers during training or not? In supervised learning, the model is trained using input-output pairs. Each training example includes both the data and the correct answer. The model's job is to learn a mapping from inputs to outputs so that it can predict the correct answer for new, unseen data. You can think of supervised learning as learning with a teacher who provides the right answers during practice. A classic example is email spam detection. The training dataset contains emails along with labels such as spam or not spam. The model learns patterns that correlate with each label. During training, the model makes predictions, compares them to the true labels, computes an error, loss, and updates its parameters to reduce that error. Over time, it becomes good at predicting the correct label. Supervised learning is typically used for tasks like classification and regression. Classification predicts discrete categories, such as whether an image contains a cat or a dog. Regression predicts continuous values, such as house prices or temperature. The key requirement is that labeled data must be available, and often in large quantities. Unsupervised learning is fundamentally different because the data does not come with labels. The model is given raw input data and must discover structure, patterns, or organization on its own. There is no explicit correct answer during training. Instead of learning a mapping to known outputs, the model tries to understand the underlying distribution of the data. A common example is customer segmentation. Suppose you have purchase behavior data from many users but no predefined groups. An unsupervised algorithm can cluster users into groups based on similarity. The algorithm is not told what the groups should be, it discovers them from statistical structure in the data. Clustering and dimensionality reduction are two major categories of unsupervised learning. Clustering groups similar data points together. Dimensionality reduction compresses data into fewer variables while preserving important structure. Both aim to reveal hidden patterns rather than predict labeled outcomes. The training signals differ sharply between the two paradigms. In supervised learning, the loss function measures how far predictions are from known labels. In unsupervised learning, the objective is usually indirect, such as reconstruction error, likelihood maximization, or similarity preservation. This makes unsupervised learning both more flexible and often more ambiguous to evaluate. Data requirements also differ in important ways. Supervised learning typically requires high-quality labeled datasets, which can be expensive and time-consuming to produce. Unsupervised learning can leverage large amounts of raw, unlabeled data, which is much easier to collect. This is one reason unsupervised and self-supervised methods have become so important in modern AI. Evaluation is usually more straightforward in supervised learning. You can compute accuracy, precision, recall, mean squared error, and other metrics by comparing predictions to ground truth labels. In unsupervised learning, evaluation is often more subjective or task-dependent because there is no single correct answer. You may rely on proxy metrics or downstream performance. From an optimization perspective, supervised learning tends to be more stable because the objective is clearly defined. Unsupervised learning often involves more fragile objectives and can be sensitive to hyperparameters, initialization, and assumptions about the data distribution. In modern large language models, the boundary between these paradigms has blurred somewhat. Most large models are first trained using self-supervised learning, which is technically a form of unsupervised learning but with automatically generated labels. For example, predicting the next token in text uses the text itself as the supervision signal. Later, models may be fine-tuned with supervised learning using human-labeled data to improve alignment with desired behavior. In practical system design, the choice between supervised and unsupervised learning depends heavily on what data you have and what problem you are trying to solve. If you have reliable labels and a clear prediction target, supervised learning is usually the most direct path. If labels are unavailable or the goal is exploratory pattern discovery, unsupervised learning is often more appropriate. The most important intuition is this: supervised learning learns to predict known answers, while unsupervised learning learns to uncover hidden structure. Both are essential tools in the AI toolbox, and modern systems often combine them in layered training pipelines.
If you find this video exciting, please like, subscribe, and turn on notifications.
Let's take a deeper and more technical journey into supervised versus unsupervised learning. Although the basic distinction is simple, the practical and theoretical implications are rich, subtle, and extremely important for anyone working seriously with modern AI systems. The difference is not just about labels, it touches data economics, optimization behavior, representation learning, evaluation methodology, and even the future direction of AI research. At the highest level, supervised learning is about learning from examples that include the correct answers. Each training sample consists of an input and a target output. The model's objective is to approximate the function that maps inputs to outputs as accurately as possible. In contrast, unsupervised learning operates without explicit target outputs. The model receives only raw data and must infer useful structure, patterns, or representations from the data distribution itself. This distinction sounds straightforward, but to understand its full significance, we need to examine what learning actually means in machine learning systems. In supervised learning, the problem is typically framed as empirical risk minimization. You assume there exists some underlying function f that maps inputs x to outputs y. You are given a dataset of paired observations drawn from some unknown distribution. The model, parameterized by weights theta, attempts to learn a function f theta that minimizes the expected loss between predicted outputs and true outputs. Because the true data distribution is unknown, the model minimizes the empirical loss over the training set. This gives supervised learning a very concrete optimization target. The loss function directly encodes the task objective. If the model predicts incorrectly, the gradient signal tells it exactly how to adjust parameters to improve. This tight feedback loop is one of the biggest strengths of supervised learning. The training signal is dense, explicit, and usually well aligned with the evaluation metric. When supervised learning works well, it tends to converge reliably and predictably.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.